for you. And today we are starting with a lecture by Ivan Kireev from our partners. He is a head of the Deep Learning Center at Sber, and he will be talking to you about how should we deal with event sequences data in the era of massive data. And also you can see that there is a generative bar in the title. So let's see, and let's invite Ivan closer to here. Yeah.
Hello. Nice to see you. Uh, I am. I will talk about uh, event sequence data, how to work with it, how to process it with deep learning models, and how to integrate it with like large language models. Uh, about me, I'm 8 years in machine learning. Now I'm head of deep learning center in Sber Lab, and we uh, uh, apply scientific. We make a practical R&D for Sber for our business. So we joined science and business in our practice. So, this is about Sber Lab. Now it's the name of this unit is Practical AI Center. So we use both of them. And this is short information about lab. Um, and here is links to our community, our GitHub. You can join us and see something about us. So let's go to presentation. I split this lecture in 5 parts. We start with introductions, then we talk about specific methods and architectures for event sequence data. The next step is connections with LLMs and conclusions. The first the who can name the most amazing results of last year in machine learning in artificial intelligence? I think this is large language models. They make a very big improvement in the last years, and I think now it's most amazing tools because language models can talk like a human. They can draw the pictures very well. They can work with both of these modalities. You can ask the model to draw some pictures and he do it. The key success factors of this is uh, the, the most important is key success factor is the large usage of visual and text modalities in the world. Any task can be described in as a natural language text. So many tasks can be described in as a text and provide it to language models. And these models learn it with many texts, can share his this knowledge, this word knowledge, and generalize his word model. Also, the progress of technical research can allow us to make this model bigger. We have effective architectures, I mean transformer layers with attention, and these models can grow can become very big, and this allow him to learn many information. But when we go to enterprise data like finance, telecom, retail, we see that many data is not a text. This is a structured data like a tables or a journal of, I mean, logs of some events. Here, an example of such data, it's look like tabular data, and we have a rows which are sample represent sample data, and columns which have features. There is many types, different types, numerical features like amount, for example. Here there is time features and some categorical like currency or type or MCC code. So it looks like tabular data. The one main difference is in the sequential data we have a object is not one row. The object which we want to model is the set of rows which are grouped by some ID. Here is a client ID. So we have some client and we see the many rows joined with him. These rows can be ordered in temporal with the temporal order, and this is the main, I think, main challenge for work with this data. There are other examples, and not only card transactions. Event sequence data can be receipts logs. It can be medical records, music playbacks, and others. And on the slide, there is examples of such data and practical task problems which can be solved on it. The link is a PyTorch livestream library where you can see the examples with the code and links to the data, and you can try to work with it. One more feature which the event sequence data can be multimodal. Means that one object client, for example, have not only one sequence, they can be many sequences of different origin which are linked with this client. Here, an example of multimodal banking dataset, which have 4 different modalities for one client. Here, transactions, financial transactions, GeoStream, it's the geo points of places where this customer were in the specific time, and embeddings of dialogues of this customer with technical support. The target for this dataset is purchase history. It's for different products which customer can buy, and you should predict which product customer will take, and you see the history. So you have 4 different sources, temporal distributed, and you should make some model which see together all of these sources and make predict. One more way to think about sequence, compare it with different domains. Here, the most similar domains for example, the most similar is tabular data. The key difference is the temporal dependencies in event sequence, but the way of work with features is the similar. The next is NLP. Natural text, the opposite side, we have text is a sequence of tokens, and this similar event sequence. But tokens are it's only one type of features. So this is we can look at like categorical features. Events are more complicated, and they have many different columns in each event. Time series also looks like event, but often in time series, often the sequence are regular, and but financial transactions can be usually irregular. So and time series have many numerical features. Yeah, and this is different. Sequential rexes, I think the most similar to event sequence, and the key difference is the problems which when for which we apply the modeling. In Rex's algorithms, we usually should rank the predicted next items to recommend them. And this item can be the dictionary of these items usually very big. In event sequence, there is the other problems. Usually, we should classify all sequence, or, for example, find the fraud events, or find anomalies, and something like this. So we start from large language models, and they work very well for many tasks, but for sequence they have some gaps. The first is the transfer from structured format to language. Here an example how to present the structured information for a language model. This is just a text, and the you can see here is only three fields, three features, but for language model it's about 15 tokens. Language models should see the structure of this record. So the separators, links, field names, and this is very structured information, which natively processed during the classical deep learning models, but it should be additionally learned in language models. The next challenge is when the events, the count of events become big. Each client have many events in his sequence. It can be 10,000, for example, and this is very similar text which are repeated many times when we describe it like a text, and it's difficult to find some important information in this very large text with some structures. And the last challenge is special information which are stored in our data. When we talk about enterprise application, we have a very many data in our system which can be used for model the process. Language models don't know how it works inside this application. They have only common knowledge, and it's it's a challenge for language model to understand what exactly what knowledge is inside of this structured tabular data. You know, language models work well for tasks which are for new task, and they of course can work with any data, and usually the quality of these solutions is good, but specific methods is better. Maybe 1 or 2% accuracy. It's a small improvement for specific models, but it's very big amount in the as a money. So the little error model metric drops is a very big exposure. And the enterprises choose the model which work better. And now it's not a language models. So we see that structured data have a specific approach to work with it. And let's see, let's overview this. The first is architectures, model architectures. The first step is encode events in our input data, which are tabular. For category fields, we can use learned embeddings. Here, an example of pre-trained embeddings for language, but we for structured data we can learn our self embeddings. They will not be so it's not be so nice example like with words, but it will be good embeddings for modeling. The next step is numerical features. The simple way is model it like identity field because neural networks can't work with numerical data. But when we talk about full transaction, we see that categorical fields with embeddings have more dimensions in the final representation. So embeddings can be 4, 8, or maybe 100 the dimensional, and numerical features only one. And this is the thing to improve this. There are methods which can show numerical fields not like one dimension, but like some vector with many dimensions. And one of this example is trigonometrical functions which different amplitude and phase, which can embed numerical fields like in many dimensions. What the second way is piecewise linear encoding, which looks like binarization, but each bin have a linear dependency inside of it, and it's more precise information, provide precise information about input data. And the last is the time features. The simple way is describe the time like some time or calendarical features like day of week, day of month, hour. And this is one way. The second is use some architectural improvement to model time. Here an example of a paper where when the positions of related positions of image patch image on the pictures is provided to attention layer, and we can do the same for event data. So we can model, we can provide time deltas for each sequence to attention layer and model it. The next way so now we have a representation for each event in the sequence, and the next step is model the whole sequence. There are some ways to do it. The first simplest way is use pooling layers. It can it help us to work with a sequence of different lengths, and it's important features. But this approach miss an order information, and it's not good for us. The next way is a convolution layer. He can model the time because each convolution core work locally, and he sees the order and time of features, time of events. But large context missed in this approach. If we combine the previous pooling with convolutions, we can have a, I think, nice architecture which will be modeled and locals and global patterns in the sequence, and it can be work well. One more options is use convolutions with continuous time. It's the time deltas use it as input for convolution layer, and the model can use not only order of sequence but also intervals between them. See the very frequent events or the time when no events was happened, for example. Recurrent neural networks can natively work with sequences, and they can model I think very difficult patterns in our data, but they have some limitations. When the sequence are long, this architecture, this model can forget very old events because they are in the begins of very long chain of layers, recurrent layers. Also, this iterable processing of data limit us to parallelize it, and we cannot use the difficult to make this model bigger and faster because of its terrible nature. And the next now it's most flexible network is a transformer layer with attention layers. This approach can model very complex patterns in the sequence. They can work with short and long sequence, and the main advantage of this architecture is the possibility to make parallel executions during the training and inference. This requires many memory and computational resources, but it's not a big deal to provide it. It's only it's not a technical issue. This flexibility requires more data than the previous approach, but we have this amount of data, and it's also not a problem. One intermediate options is state space model, which can have more internal hidden parameters than recurrent networks, and it's work faster than transformers. But I think now it's a little bit limited usage of this types of model. So when we see the architectures for sequential processing, we see that transformers works have a most promising way, but they require resources and the data. So the next step, now we have the model, the architecture, which can process our sequence data. Now we should train it on our data. And when we remember why language models work very well, we see that many of these thesis can be applied to sequential data. For example, we can use scalable architectures like transformers for event sequence data. We can train it with all big data which we have. Only one limitation, the format of structured data is different in any application, and we can train only a narrow model for only one source, but it also can work well. There are two different ways for pretrain. The first is generative methods. In this type of methods, we try to precisely reconstruct some part of input data to model his structure. The first old here will be the methods which can be applied for sequential information. we can adapt word-to-vec model to our sequential data. For example, sequence of banking financial transactions. This approach can learn the context in the data. And for example, we can see that there is some dependency between withdraw money in ATM and spending the money in supermarket. It can be closest events in the sequence, and this model can see the dependency between of them. But this approach can provide the embeddings only for events, but not only for all sequence. And this limited us to in usage. This. The next step variant is after encoder models. I think this is amazing idea when you fit all information about your object in intermediate latent representation. And this information is can be used to reconstruct this object. So all information about it is inside of this hidden vector. The problem is that approach works only for small data in the simple cases. When we try to apply it to more complicated case, it's work not well. The problem for sequence is the loss for the reconstruction loss. Our loss function should model should provide an error of reconstruction of all sequence. It means it should be the same count of events, the same order, and the fields inside of each event. It's a very difficult task to provide to make these loss functions for complicated objects. But we have try to make it simpler. We can reconstruct not only all sequence, but only one event. We we can use the idea from BERT model. We mask some events in the input sequence, and we try to reconstruct them. The next way is we can mask the not the events inside of sequence, but the next events. So we will predict the events which not exist in the input data, like GPT model. And we can also try to, if we talk about the methods which work with only one event, we can remember the replace token detection pretrain technique from NLP, when we replace some events or random or events from other client, and the model should find which event in the sequence are original and which are inputted from other sequence. The second way is try to model not only one event, but whole sequence. And here is two examples of also from NLP. We can split our sequence into small parts, and we ask the model to predict is these two parts are from one sequence and they are provided in correct order. And some sequences in the train input train data set are have a correct order, and some are shuffled. And the model should say which where. We can also combine this and previous approach to make more complicated learning task and have a more informative embeddings representation. The next approach is discriminative methods. Here we don't represent the precisely the original object, but we should learn the bounds in the vector space which can differentiate one object and another. Also, we can find describe the similar or dissimilar objects in the embedding space. Here the methods for developed for event sequences which use this approach. We have sequences from different clients, and we make the random subsequence from them. We encode it with some network. It can be a recurrent layer or transformer or anywhere. And the embeddings after this encoder should be closer for sequence from the same client, and should be different if it's a different clients. This way can can provide good representation for client because here the learning work force to be similar the small and big sequences, and we have a strong robust encoder. During this learning, we should describe which examples are non-similar. It's negative samples. Usually we use the samples from different clients, but it can be very simple task because usually clients have a different behavior, and his embeddings are not similar at the start of learning. And to improve the learning process, we should find the difficult samples for our learning. That means we should find these clients which are different, but we looks like similar, and try to make embeddings for them different. The next way is the problem with finding negative samples when we mention all clients are different is usually we want to find we want to mention clients not like all they are different. Some of them is similar, and we should find it. And we don't to name it like the different client. We don't want to provide it like negative samples. And this why the negative sampling can decay the performance of our model. And there are ways to work without negative sampling. The previous approach try to make different the rows, samples of, clients in the batch. Here we try to be different features of embeddings. This method try to decorrelate features of embeddings, and this allow us to avoid negative sampling and make a good representation. This method requires the precise tuning, and it can be difficult to learn it. The one more problem with previous methods, they don't learn the temporal patterns, the dynamics in the sequence. They mention all subsequence from the client is the same. Doesn't matter which time interval it was sampled. Contrastive predictive coding try to solve this problem, and it's explicitly try to predict next samples in our sequence, and they do it in contrastive way. This looks like GPT model, but the loss is not a representation loss, it's a contrastive, because we predict not the original sequence, we predict the embeddings of this original sequence. Also, they can be other methods can be modified to be contrastive. And this allows them to work with very complicated input, which can be difficult to reconstruct. So this is an example of WAV2VEC model, which work with audio sequence. So here we should we have two groups of methods: discriminative and generative, and we see the strong and weak aspects of these ways. When we apply it to sequential data, we can see that precise representation of input in generative method should provide a more precise representation of local patterns in the event sequence. It means that these generative methods should work better with tasks like which requires the local local dependencies in the data, like fraud detection, prediction of next events, etc. Discriminative method work better with whole object. They don't see the details inside of it, but they can describe all object better. And apply it for event sequence, it's means that the classification or segmentation task for a long sequence can be better solved with discriminative approaches. We can try to combine it to make some hybrid architecture which will be work well in both cases. The one more challenge for modeling sequential data is multimodal data, and there are many strategies to use many input sources, align it with along one time axis, and more complicated approaches which are use the links between the events from different sources can make more informative representation for the data. Here is a survey some methods for multimodal data, and many of them could make the good pretrain for sequential model. And the last point, it's how to we start with good work of language models for many tasks. They have external knowledge, and in other side we have narrow models for sequential data, and we want to make some use the benefits from both both of approach to make the some hybrid models which will be work with both data language and sequential, specialized sequential. Here are some examples of these methods. The first steps. We here the model which try to repeat the language model approach, but without language, without natural language. Here, the model, this model pre-trained on only structured data, and this model, one pre-trained model, work without fine-tuning for any structured tabular data set which you have. During pre-training, there are many synthetic tabular data sets provided to model context. So input of the model is all trained data set with features and targets. And model should learn not only the dependencies in one specific data set, they learn the way how to make and how to model the dependency between target and features. And what this approach limited only by the patterns which we provide in synthetic data. So we should think about the patterns which model will find in which should find in our data sets, and it only limited real world. It's bigger than the synthetic data. So this model should work well only with the patterns which are provided during the training. But it we can extend it iteratively and make this model to work better during the time. The next way is combine language and structural model. Here we have two different network. One is for language. The second is for sequential data. Is encoder model, and we learn an adapter which connect the encoder, join encoder and the language model space, internal space. This as a result, this model can use the natural language for describe the task which we want to solve on the sequence data. The limitations is looks the same as in the previous approach. We need to have the training data set, which now are synthetic data, because it's we don't have an original real world examples when sequence are described with some text. We don't have these pairs, and we should try to some the different questions or the patterns of links between text and transactions. The last models work with structural data as a text. This is a case from recommended systems. The history of interactions client and items are described in a text format, and these texts are provided to language models, which make an embedding of this interaction history. It's work well for recommendations because there are many items, many big dictionary of items which can be described in the natural text format, and language models can work well with this data. Also, this approach solves the problem of long context, long event history. Here, the two strategy to the one of them is a recurrent strategy when the history is split on some chunks and then recurrently provided to language model to make a summarized description of history. So when we talk about processing and modeling of sequence data, we see that there are some strategies to work with to learn the small narrow model, domain specific model, and this approach work well. Also, the language models which can bring external knowledge to our data, and the next step can be the join this mix this to this approach. The first steps are done. We see that they are work, but have some limitations, and this area should be researched in the future. So it's all. Here is a link to our PyTorch livestream library, where we can see many of examples of models which were in this presentation. So my contacts Do you have any questions about event sequence or pre-training methods?
Thank you for the talk, Ivan. Some of the methods you described were looked to me somewhat disjoint in the sense that they attempt to solve a particular task, like for example, a recommendation of some item that could be sold or not sold. I was wondering if there is a integrated approach as Bear to build an attempt to build like something like like a digital twin of a person that integrates all of the possible information, all of the touch points of the client with this Berika system.
The digital twins can be modeled with such approach. No, it should be generative model because twins mean that we can model the future behavior of our client, for example. Also, the multimodal approach required was one client. It's not only transactions, it's many different digital trace associated with him. We try to make this approach, implement this approach in our work, but and some results there is, but I think it's there are many future work because the quality of predictions it's not it's limited. It's we cannot precisely reconstruct the digital trace of client because it's very noise information.
And what about so-called human centricity, like the человек центричность? Do you attempt to, I don't know, like introduce some goal, which is like if the person would do that, he would achieve his like midterm or long-term goals? Do you somehow, I don't know, like make it a part of a goal for learning, or
when we talk about human centricity, we should describe this in terms of model metrics, which are we want to make our clients happy, but we should measure this happiness, and this is I think not a machine learning problem. It's a process, business problem to describe what is better for our clients. When we have this metric, it can be lifetime value, maybe customer lifetime value, for example. If we have this this property, we can measure it, we can model it.
but you don't use it like if this person, like for example, you could use it in a recommendation engine, like let's recommend this person this thing, because if he would use it, it would move him closer to his final goal, and he would be happy in the end, even if he doesn't understand it now, For example, we understand it better than this person does, so we somewhat push him into this direction. And no,
we try to model it, but this is a complicated task because it's like what if analysis. We have only one way for each client. We don't have an alternative history. What was, what will be, what our client will be done if we make some treatment. We have only one way of this, and this is a make this task more complicated. But we try to model it. It's I think one of application of these event sequence model approaches.
okay, thank you.